All right, welcome to our last session for the day, which will be waveform sensing for high contrast instruments. Our very first talk would be given by Noor Skaf. It will be about high contrast imaging waveform sensor referencing from coronagraphic images. Okay, Noor, you can go ahead.
Thank you very much. Good morning, good afternoon, everyone. It's a pleasure to be here. I will be presenting essentially two main papers that I've been posting on arXiv very recently, one ANA and one for the SPA conference. I'm a PhD student, third year between Paris Observatory and the Super Telescope in the SPXO team with Olivier and Anthony Bocaliti. All right, so I'm gonna first introduce the problem that I'm gonna be talking about today. One of the main challenge of high contrast imaging of exoplanets is the speckle subtraction. So when the adaptive optic loops is running after there is atmospheric residuals, then there is several optics in the optical path that induce some aberration, what we call the non-common path aberrations. And as a result, in the focal plane images, there is a bunch of speckles which are really hard to differentiate, with the planets. As we can see here in the image on the right-hand side, exoplanets and speckle really look alike, and that makes it a lot more challenging to do exoplanet detection and characterization. And speckles are a combination of atmospheric residuals and non-common path aberrations, which are static and dynamic with different spatial frequencies as well. So the main point is then, what is a good reference? What is a good calibration of the adaptive optics loop? What is a good point of convergence of the AO loop? And so in other words, the question is, what is the wavefront sensor ideal reference that includes all the aberration, including the non-common path aberrations? And in other words, that means what gives a flat wavefront sensor? Usually the reference of the wavefront sensor is measured with an internal light source in the instrument, but this ideal reference is continuously evolving. So there is really an essential need of a continuous way to measure the wavefront sensor reference on sky, because as I mentioned before, the non-common path aberrations are some of them are dynamic and quasi-static. And I really would like to emphasize that what is put as a reference on the wavefront sensor is not the ideal reference. This is the whole problem here. And so the goal is really to find what is the closest from it and to have the adaptive optic loop converging towards an aberration-free state. So for that, I will introduce the Doctor Who algorithm, which stands for direct reinforcement wavefront heuristic optimization. Yes, we're very proud of the name. And while the adaptive loop is running, the point is to update the pyramid wavefront sensor reference. I'm saying pyramid wavefront sensor, but it can be any it works for any type of wavefront sensor. It's just that on SPXO it's a pyramid. So here I will describe the algorithm. So while the adaptive optics loop is running, we save the telemetry of the focal plane data and the wavefront sensor data. So the first step is then to have, let's say for a 30-second period, to the blocks of telemetry data of 30 seconds period, we need to synchronize those blocks, to synchronize the wavefront sensor and focal plane telemetry. So we end up having two blocks synchronized for both focal plane and wavefront sensor data. And this is where the core of the Doctor Who algorithm comes into play. The following step is to take the focal plane block and to measure the quality criteria for each image of that block, which can be the Strahl ratio, the contrast, the intensity, you name it, whatever you prefer. And then we take the best 10% images of those based on this quality criteria. And we take the corresponding pyramid wavefront sensor measurements corresponding to those 10% best PSF focal plane. So as a result, we have an equivalent of 10% wavefront sensor images corresponding to the best focal plane images. So it really is a form of loci imaging, and from that, then we find a new reference, which is the average of the best wavefront sensor images. This final reference is put as a reference in the adaptive optic loops, which changes the point of convergence of the loop, and as a result has a direct impact on the focal plane images. Here I put PSF, but can work as well for coronagraphic images. So overall, Doctor Who is completely transparent over the adaptive optic loop, besides the fact that it continuously updates the reference every 30 seconds of the of the wavefront sensor, and therefore changes the point of convergence of the AO loop. All right, so I'm gonna first present some non-coronagraphic results. First, I did some simulations with the Compass simulation software. It's an end-to-end adaptive optics simulation tool, super powerful and super great. What I did is I simulated SCALE on it, and I injected 30 nanometers of NCPAs with a random combination of the first 12 modes, and wanted to see whether Doctor Who would be able to correct them or not. So what I see when I look at the evolution of the STARLOC ratio for 15 iteration here, so 15 iteration of 30 seconds, I see that the STARLOC ratio increased, and most of the correction is done at the first iteration. It takes quite a long time to do on simulation. That's why I didn't do more than 15 iterations. But then I wanted to see how much of those of this correction actually correspond to what I have injected at first. So in the blue, in blue here, you can see the plot of the NCPA, what I actually injected, and in purple is the mean of all of the references that Doctor Who found. So we see it's actually surprisingly accurate compared to what we have injected, and that the wavefront sensor did not know at all, because it's not in the wavefront sensor path. So as a conclusion, each injected mode is actually recognized and corrected by the first iteration, which is a huge simulation result. So then we did on Sky tests, and over a 10-minute run, we did 20 Doctor Who iterations of 30 seconds each. And we used the Vampire instrument for the PSF at 750 nanometers. The atmospheric conditions were actually really good that night, so we got those results. But before talking about that, I will introduce a new quality criteria, which is the flux concentration, which is defined as follows: as the absolute value of the pixel value over the norm of it. And in a nutshell, it describes the concentration of flux, and it looks like at all the pixels, not only not only the peak, which is the main difference of the STARLOC ratio, and it's a relative quantity, so it depends on the number of pixels considered. And the whole point is to maximize it, because the more aberration, the more spread the light is, and therefore the smaller is the flux concentration. Here are the results over the PSF over the 10-minute run. So on the left-hand side, it's the PSF before running Doctor Who. So you see, it's kind of a blurry thing. The first iteration we already see in the middle. We already see the area rings that are a lot better resolved. And on the right-hand side, we see something that looks a lot more like the simulated perfect PSF on SCALE with vampires at this wavelength. So that was quite an encouraging results. Regarding the flux concentration, this is the evolution, the plot evolution of per iteration. So we see that most of the correction is really done by the first iteration. And after the 10-minute run, it still didn't seem to have fully converged. So it means there is still room for improvement. All right. And once that was done, we looked at the evolution of the wavefront sensor reference to see what could be the modal projection. So we did project the reference over the control matrix to get a contribution of modes. So what we see essentially, as you see here on the left, is the lower the aberration modes that are the main contributions. There were things happening for the higher the modes, which makes sense. We don't actually try to correct them here. And the main correction was actually on the focus with a almost 14 nanometer RMS correction. All right, so now I'm going to be presenting some coronagraphic results, some new one compared to the ones I have presented at the SPAE conference. So the main difference with Dr. Who in coronagraphic mode, in non-coronagraphic mode with PSF, is that we just changed the quality criteria. Instead of looking at the stir ratio or the flux concentration, we look at the intensity or the contrast, and we try to minimize it. The main challenge in that case is actually the tip tilt, because as during the observation, there is tip tilt that makes the coronagraphic image brighter in intensity, which makes the selection criteria more challenging. So we did further test on Sky with the SkyXO instrument on September 10th with a fast infrared camera. Here are some results with on top the coronagraphic images. So we see that the contrast is actually looks a lot better. On the bottom plot, it's the evolution of the intensity. There is still a few things that I am not fully sure to fully understand on how is going on, but this is all work in progress. However, as we see on the coronagraphic images, the center part is what seems to be the best correction. And so, in fact, most of the correction happens in the center, which corresponds to the lower order modes. And this is expected because we expect the non-common path aberrations to be essentially lower order modes. All right, quickly some perspectives. Something that I've been working on as well for some time is the parallelization of Dr. Who in zones of the focal plane image. This is based on a principle that a speckle pattern may be decomposed in the sum of plane waves with Fourier transform. So when in the pupil plane you have a sine wave, in the focal plane you have a pair of speckle. So basically, the point is to take advantage of it and try to correct speckles pretty much one by one. So by dividing the PSF, I'm not sure you can see my mouse moving. No, I don't think you can. So anyway, on the left, as you see, we pretty much divide the PSF, and we get intensities per each of the zones. We then look at the Fourier filtering, of the wavefront sensor images per zone, and we get a new, pretty much a new reference per zone. And the sum of those zones, the sum of those sub-references is then applied as a new reference on the focal on the wavefront sensor reference. So this is still work in progress. Don't have much results to show you yet. However, so the whole point is to basically get zones of variable sizes. The goal is to go over 1 lambda over d to treat speckle individually and find out the zones where the intensity does not decrease, and eventually conclude whether it's a speckle or possibly a companion. All right, very briefly, we'll conclude. So the Dr. Who algorithm is robust. Actually, it cannot really go wrong. According to my test, it's very flexible because it can basically be working on coronagraphic images and non-coronagraphic images with Schachertmann or any pyramid or the wavefront sensor of your choice. It doesn't make any linear assumption. It does not rely on any other model. Therefore, it can be used with other wavefront control techniques. There is no action on the AO loop beside the reference update, so it's very transparent to that. It works on faint stars, and non-common path aberrations are recognized and compensated for. The downside is that we do need a fast focal plane camera, which not all instruments have, and it needs fairly decent atmospheric conditions to be actually able to be effective. Otherwise, it does not make things better, but it doesn't necessarily improve them. And as I mentioned, there's numerous ways of improvements. And thank you very much for listening.
Wonderful. Thank you, Noor, for your talk. And we have a few questions. I will read them to you. So Anthony Verdes is asking, if I understand well, you need fast science measurements on the order of 2 kilohertz that you couple with the corresponding wavefront sensor measurements and keep the best 10%. How can you extend this technique when the science measurements are long exposures?
You can't really actually. You can, I mean, you can go lower than 2 kilohertz. You can go, I mean, with the vampires, for example, we were running at 500 hertz. All that matters is that it's fast enough to actually have a diverse representation of the atmospheric turbulence to be able to compensate for, like randomly compensate, like do lucky imaging to compensate for the NCPAs when the atmosphere has specific aberration. Basically, the point is to be fast enough so that it can actually correct for the NCPAs. So I don't see, it's not really possible to do it for long exposures, simply because then that would mean you would need to average all of your wavefront sensor images. And as a result, you won't be able to have basically random correction of the atmosphere over the NCPA. I have tried with 200 hertz. It's borderline, actually, okay.
So we have another question. So from Olivier Absil, how many science frames do you usually need to make one Doctor Who iteration?
So it depends at what frequency you run. So if you have, so usually what I do is a block of 30 seconds. It can be actually a lot less, especially in good condition. You can do 10 seconds at 2 kilohertz or 500 hertz or whichever your loop frequency is. On good conditions, you don't even need that many. I mean, you will always need like a few thousands frames to have enough diversity. But then there is a play on also like, do you select 10% or do you select 1% best? It really is. If you can go like less long. You can go 5 seconds, for example, of iteration and select the best 1%. So it's very flexible in that respect.
All right. So I think we are good. Wonderful talk. Thank you, Noor. So please stop sharing. We shall move to the next speaker, which is Elsa Huby. She will be presenting STARLOC, the star tracking algorithm for the MICADO Lyot coronagraphs.
Yes, hi.
Go ahead,
is
Elsa.
it okay? Yes, okay. Thank you. Well, thank you. So I'm going to present the STARLOC algorithm, which is an algorithm that we've developed with Pierre Bedoz here at Paris Observatory to track the star on the MICADO Lyot coronagraphs. So you may already know that there are 3 classical Lyot coronagraphs in MICADO with 3 different occulting spots diameter, so 12, 25, and 15 mass. And there is a Lyot stop. And there was no possibility to include an apodized pupil, unfortunately. So these are just classical Lyot coronagraphs. And you can see here the images that have been simulated for the 3 coronagraphs in the different spectral bands that are offered by MICADO, J, H, and K. Yes, so these are the coronagraphs in MICADO. But you certainly know that if you want the optimal performance of your coronagraph, you need the star to be centered on the coronagraph. However, there are drift that can be expected during the observations due to, for example, the uncompensated atmospheric dispersion between the AO wavefront sensor working in the visible and the infrared science camera. There can be also mechanical drift due to moving optics because you know MICADO and the ELT in general are huge instruments, also due to temperature variations. So we've simulated the effect of a tip-tilt drift on the contrast curves that you see appearing here. These are 1 sigma contrast curves for CLC1 in J, H, and K. And you can see the effect of different drift level from 0.5 mass to 10 mass in 1 hour of observations. And you can see the effect is obvious for the small separations. And in J-band, for example, you may want to stay below the 0.5 mass drift, while in K, a 1 mass drift might be acceptable. But our requirement has been set to 0.5 mass in MICADO. So to achieve that, we've developed an algorithm that is based on the same principle as the Cassett's algorithm that's been developed for the vortex chronograph case. So you may recognize the typical donut shape that you obtain in the case of the vortex chronograph when there is a centering error. And the idea of this algorithm is to simply measure the flux asymmetry in this chronographic image in quadrant. And by just measuring this differential intensity, you can make an estimation of the centering error. And it's been shown that it's better to work on an area that is defined on an annulus, not on the whole image, because in your diffraction pattern, there are different components that behave differently with the centering error, and that can just bias your estimate. So we wanted to apply the same kind of algorithm to the classical Lyot chronographs in MICADO. So that's why we've developed the STARLOC algorithm. But the difference is that there is no analytical model like in the vortex case. So in order to define the parameters of the algorithm, so the analysis area, so what annulus do I want to analyze, and also the slope of the model, I've made a study. So I went brute force, just simulating a set of images with a tip tilt varying from 0 to 6 mass. And I just tested a grid of analysis area ranging from the full disk to a thin annulus. And I just, for each case, I just looked at the differential intensity behavior and fitted, so this is the different simulations, and fitted, so this is a graph of the differential intensity as a function of the centering error in one particular case for one particular annulus. And I just fitted a linear model on this data, and based on some criteria, I chose the best annulus for each configuration of coronagraph and spectral band. So I wanted, for example, the highest slope as possible to ensure highest sensitivity. I wanted the same behavior in both directions, which is not always the case because of the diffraction by the spiders. Yes, the analysis area should not be too big to avoid being biased by the science object itself. So this is the resulting optimal analysis area I've defined. So in blue are the diameters of the different coronagraphs occulting spot in the focal plane. And in dashed green are the selected areas. And the simulations you see are in ideal conditions without any turbulence or aberrations. And you can see the very different diffraction pattern that we get in the different configurations. So after selecting the models, I did a study of the performance of this algorithm in different cases. So first, the ideal cases without any aberrations. So what I did is I simulated grids of centering errors in X and Y that you can see here. and I subtracted here a reference image. That's why it's completely blank at the center. And doing so, you can see the asymmetry in the images appear. And that's what's measured by the algorithm. And I plotted the results into what I call the distortion grids, showing the difference between the true centering error and the estimates. And you can see that all these vectors are pointing towards the center, sorry, meaning that, sorry, sorry. Oh, sorry. So meaning I can't talk. Meaning that, sorry, that the centering is underestimated. Okay, so I try to go on. I've also studied the impact of static aberrations by just adding a Zernike polynomial on top of the centering error. And you can see that subtracting a reference image is quite effective to have the algorithm work correctly. And what I want to do next is simulate more complex static aberrations, including a range of Zernike polynomials. I've also studied speckle noise due to residual AO phase grains, simulated with the compass also, performed by Fabrice Vidal. And what I did is that I simulated images with different integration times to see how the speckles averages and how they impact the STARLOC estimate. So you can see here 2 examples, 3 seconds, 10 seconds. And, and the estimate I get on this whole sequence for different bins, temporal bins, so 5, 10, and 20 seconds. And of course, the longer the exposures, the less dispersed the estimates are. And we can summarize these results in these kind of plots. When you see the centering errors corresponding to the dispersion of the points I was showing earlier as a function of the integration time. And the conclusion here is that if we choose an integration time of typically 10 seconds, we get an error on the centering that is 1 mass at maximum. And I've also studied the impact of the photon noise, so converting my images into a photon number and adding a photon noise and without noise, and see how this impacts the STARLOC estimates. So again, I have my grids here, and I did 10 drawings of the noise for in each case, for each star magnitude, and you can see here how the estimates gets spreads around the mean value. And you can, in each case, estimate a mean error corresponding to the impact of the photon noise, which can be summarized in this plot, showing the error on the centering due to the photon noise as a function of the star magnitude. And what's interesting is that we can, the STARLOC estimates works up to a magnitude of 13 and even higher, depending on the chronograph and the spectral band you're using. And in the end, at last, I've also made a very basic loop study, loop simulation. So it's not a real loop simulation where I simulate the coronagraphic images. It's just a monitoring of the star, of the actual star position, including a drift rate of 10 mass per hour, and seeing how the correction and a measurement error on this measurement would affect the efficiency of the loop. So here I consider 1 mass speckle noise and 0.3 mass photon noise. And of course, if we have only a proportional gain, you see that the loop is noisy. Well, the star position is still quite noisy, but if you include integral gain, like in the graph below, you see that we can stabilize the star position down to an accuracy of 0.1 mass and a stability of 0.14 mass RMS. And that's it. The conclusions is that so the STARLOC algorithms that we've developed can stabilize the star onto the chronograph center down to the required 0.5 mass. And some simulations study remain to be done, like more complex static phase aberrations and other scene conditions, for example, or even a real correction loop simulation. And I thank you for your attention, and sorry again for my loss of voice in the middle.
All right, thanks also for your wonderful talk. Please drink a glass of water. While we read the question, we will have time for only one question though.
Yes.
We have one from Jean-Francois, which is how sensitive is the STARLOC algorithm to uncorrected petal modes or low wind effect modes?
Well, that's a good question. I think we have to simulate that. I don't know yet, but we'll have a look. We'll have a look at that. But I guess it will be biased. It will depend how we'll choose the reference image, and from that perspective, the Doctor Who algorithm seemed really interesting. Also, it gives idea to apply it here too.
Perfect. Thank you also for your talk.
Thank you.
Please stop sharing so we can move on to our next speaker, which is Rebecca Jensen-Clem. We will be talking about the status of the Planetary Systems Imager Adaptive Optics System.
Okay, thank you, Esteban. I'll share my screen. Okay, so I'm speaking to you today on behalf of a large team, many of whom are listed here, who are developing the science and the preliminary designs for the Planetary Systems Imager, or PSI. PSI is a planned second-generation instrument for the 30-meter telescope, the TMT. And the plan is that the PSI will be the workhorse instrument for high-contrast exoplanet imaging and spectroscopy. So PSI currently has a layout that looks something like this. There are several different subcomponents to the system. The light from the TMT will first be fed into what we call PSI red. This is the near-infrared component of the instrument, and this is home to the common path adaptive optics system, so our first stage deformable mirror and our wavefront sensor. From there, the light, From there, the light is split into several different paths. One goes to what we call PSI 10 for the longer wavelength observations, and the other to PSI blue for shorter wavelength observations. And PSI blue has a second stage adaptive optics system to support those shorter wavelength observations. So in this talk, I'm going to talk a bit about the initial design exploration that we've carried out for the PSI red adaptive optics system and instruments specifically, and then talk about some of the preliminary contrast performance modeling that we've done specifically for PSI red, leaving PSI blue for another talk. Okay, so I want to say a few words about the design requirements for this first stage AO system. So PSI will be located at the TMT's Nasmuth platform. So we have our input F15 beam. We have to cover a wide wavelength range in order to accommodate all of the science cases for PSI. Of course, we want to minimize the number of warm surfaces. For our first stage deformable mirror, we're basing the design on an Alpeo mirror, which has 120 actuators across the pupil. And for our PSI red wavefront sensor, we're considering a near-infrared pyramid design with 156 actuators across the pupil. So that's, of course, oversampled. And this is currently baseline for Saphira detectors. Okay, so some of the preliminary design choices that we've made as part of this exploration is that we're going to be operating in NGS mode only, and we'll then compare the results of this design study with previous work that was a combined NGS-LGS concept study for a PSI-like instrument. We're basing our design around a single off-axis ellipse that results in an F30 beam going into PSI red and PSI blue. I'll show you some diagrams in a moment that illustrate that. And then we want to co-locate PSI red and PSI 10, again, just to minimize the number of warm surfaces. Okay, so this is an image of our preliminary optical design. This was created by our Lab for Adaptive Optics director, Phil Hinz, here at UC Observatories. And what you see here is that the telescope's focus is buried down at the bottom of the screen, so you can't see that here. But the light then diverges as you move up the center of the screen to that off-axis ellipse that I mentioned. That's a 1:2 imager that creates our F30 beam. From there, the light goes back to the bottom of the screen to the Alpeo DM at the bottom, and then to the left to PSI red, to the right to PSI blue. These are dichroics that are splitting the beam, and then again to the PSI red wavefront sensor. Okay, so then zooming in on the PSI wavefront sensor arm, I want to draw your attention to the upper left part of the beam. That's where the F30 beam from the off-axis ellipse comes in. We have room for a pupil rotator and an ADC. Then coming into the pyramid arm, we have our magnified beam that magnifies the light for the tip of the pyramid. This is a reflective pyramid design. So what we have is the light gets reflected back up to a collimating mirror that you see, and then back through some holes in the pyramid mask to make the final pupil image. And this reflective design is something that we're currently prototyping here in the Lab for Adaptive Optics. Okay, so I also want to mention that we're exploring how we might integrate a 2 to 5 micron spectrograph into PSI red. And this is based on the design of SCALES, which is an upcoming instrument for the Keck telescope. And SCALES is meant to be a precursor instrument for PSI red, so we can take advantage of that design heritage. So for the PSI red version of this instrument, we'll have an imager channel and an integral field spectrograph channel, which has 2 modes, a low resolution and a medium resolution mode. So that's just a brief overview of where we are in terms of this preliminary design exploration of PSI red AO and its science channel. And please let me know at the end of this talk or follow up if you have questions about this component. Now, next, I want to move on to our simulation of the contrast performance of PSI red. And so far, our philosophy for this work has been to anchor our simulation predictions on existing telescopes on sky, and specifically focusing on the Keck telescope. So we've created an end-to-end AO simulation using the HCI Pi tool, which has been developed by Emil Poor and others. And using this tool, we first simulated Keck's near-infrared pyramid wavefront sensor and NERC2 vortex coronagraph system. So in HCI-Pi, we set up our segmented Keck aperture. We chose a night where we had a great deal of vortex coronagraphic data. So on this particular night, we noted our seeing, our wind conditions, et cetera. And we included that in our atmospheric turbulence simulation component of HCI-Pi. Now, next in our simulation, we have our pyramid wavefront sensor, which operates at Keck in the H band. And we also had a 5 lambda over D modulation radius. Here we're assuming that we're integrating for about 1 second. So we cut out the 4 pupils from the wavefront sensor, and we compute the X and the Y slopes. And a lot of this work has been done by Micah Van Coten, a postdoc in our group, who you heard from earlier this morning. So in our simulation, we then have our deformable mirror. At Keck, we have a relatively low number of actuators, only 21 across our pupil. Okay, now one of our challenges in terms of simulating the Keck AO system is that it's difficult to disentangle what wavefront errors come from non-common path aberrations inside our NERC2 science instrument, and what aberrations are coming from misalignments of the primary mirror segments themselves. So what we've done in a preliminary way in this simulation is to say, let's put all of those aberrations for the moment on the primary mirror. Okay, and then of course we also have our vector vortex coronagraph simulation as well. We set up our AO control code. And just to note, we include photon noise only in the simulation. We're not currently simulating detector noise. Now, this figure shows you some representative figures and the results from a 60-second run of our simulation. So we're simulating each millisecond of the AO control loop. So we are saving at each millisecond our L-band coronagraphic image, our instantaneous PSF, our wavefront slopes, and then here for the whole run, you see what our wavefront error and our Strel ratios looked like. Okay, so as I said, we're now going to validate this using data that we saved on Sky. So in this process, we're only comparing our simulation to what I'm going to call the raw or the unprocessed contrast. So here we didn't use any kind of angular differential imaging or principal component analysis. We're just comparing to the raw contrast for this particular night. And the results are in the slide that you see here. This is the log of the contrast. This is for just an 18-second, so very short exposure, L-band raw contrast curve. So the black is our simulation and the red is our on-sky contrast. And we're not including tip tilt control in our simulation. And so that's why you see that our simulated contrast is so much better, very close to the star. So the match isn't perfect, but it gives us some confidence going forward to our TMT simulation. I'll discuss the limitations of this at the end of the talk. So for our TMT simulation, we tried to change as few parameters as possible from our Keck simulation. We of course have our different aperture and the associated sampling across the pupil has to be different. But we again set up some standard atmospheric turbulence profiles. We also did not include tip tilt in this TMT simulation. So we again had an H-band pyramid wavefront sensor. We have, of course, many more actuators across the pupil for our PSI simulation, 120 actuators. As before, we create our interaction matrix. We again put similar phase errors on the primary as we did for the Keck simulation. And then we again have a vortex coronagraph. So what did we find? This is a similar set of figures as I showed in the Keck figures earlier. We have our coronagraphic images. This time we did K rather than L-band coronagraphic images, our PSFs, slopes, our wavefront errors, and our Strels. Now, as you can imagine, it's more difficult to do a long time series with the TMT since the simulation has to be so much higher resolution. Okay, so now what I want to illustrate here is how the contrast that we predict for PSI changes when you include these Keck-like primary mirror segment errors that we included in the first part of our simulation, compared with no segment piston errors at all. So no errors is that dotted line that you see here. I'm showing you the relative contrast. It's just normalized, you see in the upper left at 0, rather than showing the absolute contrast, because this is such a short simulation, only 30 seconds. And because it's very preliminary, I wanted to emphasize the difference between these curves rather than their absolute contrast. So what this is showing us is that in a preliminary way, how the contrast might be degraded if we weren't able to control the segments on TMT significantly better than we could on KEK. Okay, so this captures our preliminary simulation work. There's a lot of work left to do. With our existing simulations, our immediate next steps are to go to longer timescales. So I just showed you 30 seconds worth of simulation. We'd like to go up to 1 hour. We also would like to understand how our contrast varies as a function of the Strel and the guide star magnitude. But more generally, a lot of the work that we'd like to do on the simulation has to do with the quality of our current on-sky data. For example, we'd like to anchor our NCPA and primary mirror error budget terms to on-sky data at KEK. But what limits our contrast at KEK is in many ways quite different than what limits the contrast at other extreme AO systems. So we'd like to also partner with other extreme AO systems with well-validated error budgets to anchor our simulations as well. So before I conclude, I just wanted to advertise some additional talks by members of our group. Coming up, you already heard from Micah Van Coten earlier today, but I hope you'll check out Ben Gerard and Aditya Sengupta's talks later this week. So with that, I'm happy to take any questions.
All right, thank you, Rebecca, for your talk. Wonderful. We already have a question for you, a few questions. So one of them is if you guys will need to develop a new Saphira detector for this for the PSI pyramid waveform sensor sampling, given that for the current detectors, maybe the amount of pixels you want across your pupil will not fit.
Yeah, so right now, this is also related to the debate between whether we'll have a 4-sided or a 3-sided pyramid. You might, if you're looking carefully, you might catch that in the reflective pyramid design here, we considered 3 pupils, and then later I considered 4 pupils. So having 3 pupils might be one way to better take advantage of that space. But we are considering current and planned Saphira designs for this.
All right, we have another question from Olivier Absil. Even though the contrast is largely degraded with segment piston, wouldn't a large part of that be removed by ADI processing because it's a static contribution?
Yeah, I mean, this is really challenging, because what we would like to do is understand at KEK how these segment piston errors affect our contrast. And to what extent are the segment errors changing over the course of an observation as the gravity vector on the telescope changes. So if you're completely right, if they were static, they might be straightforward to calibrate out in post-processing, but our concern at KEK is that they're not static over the course of a long observation. So that's something that using the Zernike wavefront sensor work that Micah Van Coten and others are leading, that we'd like to understand at KEK.
Wonderful. Thank you so much for your talk, then, Rebecca.
Thank you.
Let's move on to our next speaker, which is Olivier Guyon. He will be talking about high contrast imaging at the photon noise limit with wavefront sensor-based PSF calibration. Go ahead, Olivier.
Hello. Let me set up my screen size. All right, can you hear me? Can you see my screen?
Perfect, go ahead.
All right, thank you. So I'm going to talk about high contrast imaging at the photon noise limit with PSF calibration from wavefront sensor data. So here's the list of co-authors that have been working with me on this problem. So in high contrast imaging, our main challenge is speckle noise. We have to find a way to basically calibrate them, to remove them from the data. There are various paths to doing that. We can modulate the DM to modulate the speckles themselves and extract from that signal the coherent part of the image. So this is an example of us doing that in the lab. with this image. And there's also various passive techniques which do not require DM actuation, but they all have their disadvantages. And a lot of them require sort of perturbation to the image, which we don't want. So what I'm going to discuss is sort of an added mode to the way we do wavefront control, where instead of just taking the wavefront sensor images and data and doing a correction from them, which is shown by the red arrows here, we're actually taking after the fact, we're taking the telemetry from the wavefront sensors, whether it's pyramid wavefront sensor as shown on the left here, or some other parts of the image that's not in the high contrast area that's shown in the red box here. And from that wavefront sensor telemetry, we recompute what is the starlight in the high contrast area so that we can calibrate it, we can numerically remove it in post-processing. So some of you might wonder, well, why do that at all? We have this wavefront sensor data, we should just use it optimally to do a control and then we'll be done. There are really fundamental reasons why we want to do post-processing, and it allows us to do things that we cannot do in closed loop control. First one is some of the wavefront errors may be seen by the wavefront sensor, but cannot be corrected. Amplitude errors due to scintillation is an example. If you do work in post-processing, you don't have temporal lag because you have access to the current wavefront sensor measurement, which the real-time loop does not have access to. So that's why we try to do predictive control in real-time control. But here we actually have the real-time wavefront sensor measurement on time. We even have the future wavefront sensor measurement. So in addition to doing predictive control, we can do back prediction from the future to the present. And if we work offline, we don't have real-time computation requirements. So we can deploy neural nets and on cloud computing resources, and all of these become possible. So the motivation is that if we manage to actually remove speckles done in post-processing, we would have the sensitivity with large telescope to image Earth-like planets. So for example, if we take a 30-meter diameter telescope, an Earth-like planet in the habitable zone of M4 type star at 4 parsec, in only 7 minutes, we could pull it out at a signal ratio of 10. And that's done even though the contrast limit, the raw contrast is at about 10 to the -5. So that's the motivation. That's why we want to do that. So how do we do this? Well, here's a sort of cartoonish representation. On the left, we have wavefront sensor measurements, and on the right, we have the state of the dark field, the speckle field that we want to reconstruct. So both of those are highly multidimensional. I'm simplifying by showing 2D representation here. But the idea is to build a correspondence, a mapping, a relationship between the left and the right. So basically, for every wavefront sensor measurement we would get in this phase space, we would be able to pull out what is the corresponding speckle field and remove it in post-processing. And there are various ways to do this. You could do a lookup table, but that's probably not what you want to do because of the high dimensionality of the space. You can do a sort of locally linear derivations. You can deploy neural nets. I'm not going to go too much into that, but the basic idea that I want you to remember is shown on this cartoon. So what could go wrong? Well, there may not be a one-to-one relationship between the wavefront sensor and the residual speckles, in which case we don't have a solution. So this is what shown in this cartoon. Similar wavefront sensor measurement could lead to different speckles in the focal plane, and then we're sort of dead, right? We can't do anything. So that's what we want to check first. Are we in that situation? So there is some encouraging work. So here is work that was done using Skexio data by Barnaby Norris and Alison Wong of using neural nets to reconstruct the PSF. So I'm just going to play a quick video. This is on sky data, pyramid image on the left, the truth image on the right, the predicted image in the middle. And this is using a neural net in the visible, where things like this are quite challenging to do usually. So the residual wavefront error here is, if you look at the PSF difference, it's on the order of maybe 10 nanometer or so. So it's working pretty well. So if I freeze, you can see that the predicted image matches the truth image pretty well, but it's not perfect, right? I'm just going to freeze a few of those. And this one is a particularly bad example. And there's multiple problems with that. It's a far we have a far way to go from this test to actually doing really high contrast imaging. We're just predicting the PSF here. We need to get to sub-nanometer precision to really do high contrast imaging. So we ran an experiment on the Skexo bench, and this is the experimental setup. We dug a dark hole, which is shown on the top here. So I worked especially with Kuhn and on this. And so that's our wavefront, and our wavefront sensor area is in the bottom here. So we used what we call linear dark field control sort of setup to do this. And the idea, the test is, can we compute what's on the top from what's on the bottom? And so this is our results. And so here I'm showing one of those clusters that I showed you. So on the left is all of the data, and on the right is a cluster, and the movie is spinning through images. You can see that it works actually quite well. And so we managed to stabilize the speckle field. And so the clusters are very tight in the sort of wavefront sensor to science focal plane image space. So that's extremely encouraging. And if we look at what we've done, we achieved a 30 times gain in the variance of the speckle field in the dark hole, which is quite a big gain already. So that's very encouraging. So here, same stretch. On the top is the average image, which is not really what we're interested in. The bottom is the variance. You can see that we actually reduced considerably the variance in the dark hole. So now I'm gonna discuss what to do next. The ideal setup, we believe, to do this type of work is a photonic nuller. Photonic nuller basically couples the starlight from the pupil of the telescope into waveguides, and then you go into a chip where you do the nulling, so it's the equivalent for chronograph, but also the wavefront sensing at the same time. And then you can disperse in wavelength in the back end. The reason it's optimal is because it has very good wavefront sensor sensitivity, but also there's essentially no chance for non-common path error between the wavefront sensor and the null, because it's all happening in the same chip. So you should get a very complete measurement in the back end of the state of the input to do this calibration. And it's also a way to get very small inner working angle sort of chronography. So we tested this on the Glint instrument, which is installed on Skexo. So this is the picture of the Glint box sort of stuck on the side of Skexo. And this is the box open. So I'm not going to go into the optics themselves, but this is what the data looks like. So this is a frame, typical frame coming from Glint. Wavelength is on the x-axis, and each line is essentially an output of the chip. Some of the outputs are wavefront sensor outputs, shown by the green arrows. So those of you working in interferometry would call this a fringe tracking output. And some of the outputs are null outputs. And so the interferometrists call this a null output. We would call it, chronograph people would call it a science pixel, essentially a dark science pixel. So we did the same algorithm. We tested the same algorithm in the lab on Glint, and on the left side is without calibration, and the right side is calibration. The calibration uses the blue box, which is the wavefront sensor inputs, to calibrate the red box, which is the null output. And we can see that there is a very significant gain in both the null depth, but also the null stability. So average is on column C, and column D is the standard deviation. So not only the null is very deep, but it's also very stable compared to the no calibration case. This is in the lab, and then on Sky, this is on a star, Alpha Boo, Arcturus, fairly bright star. And it also works very well. You can see that with the calibration, the null depth is significantly deeper, and the standard deviation is actually undetectable. We're basically below the readout noise and photon noise in the dark hole or in the null output with this test. And you can even see that we resolve the star, which is not too surprising. It's a fairly large star. So it's darker with the short baseline null than it is with the long baseline null. And so this is all looking quite promising, but there's of course a lot of work to do. But what I want to conclude with is the fact that this photonic nulling approach to PSF calibration is interesting because it gives us deep nulls, good wavefront sensor calibration, but also very small inner working angle. And if we achieve all those things at the same time, with a ELT-sized telescope, we should have access to a large number of habitable planets, which are shown in this angular separation versus graph here. So that's our long-term motivation. Hopefully not too long-term. And my conclusion slide, the takeaway messages is all Starlight is useful. Don't throw it away. You should store it because someone might be able one day to actually figure out how to use it to actually recover, to remove essentially your noise from the science data. And you should record as much as possible it at high speed multi-wavelength so that speckles basically can't hide. And the last point I made is a photonic nuller is an attractive option to implement this. We believe superior to standard sort of Fourier plane coronagraph because we get small inner working angle, very sensitive wavefront sensing at the same time as we get in the same device as we get the nulls, and we get that as a function of wavelength. So that's my conclusion slide, and hopefully we have time for a couple of questions.
All right. Thank you, Olivier, for your wonderful talk. We are waiting for some questions. I don't know if someone has written one down already. No one yet. So I have one. So when you say that we should record the telemetry at high speeds, so for how long? I mean, I know you would like everything to happen at very, very fast rates, but how long it's feasible? I mean, or good enough?
Well, so let me answer two parts of the question. The high speed requirement only applies if you have a nonlinear response in your wavefront sensor. Basically, if you have a linear wavefront sensor, and a linear focal plane, you could go slower because if you have a one-to-one mapping and you apply a linear sum on top of it, you still have the same mapping. The high speed comes from the fact that the focal plane is not a linear encoding of the wavefront sensor information. So you have non-linear relationship, which means that you can't take if you have a linear mapping but you apply an average sum on one side, you don't land in the same spot on the other side. So that's why you need to go fast fundamentally. And then I think the data storage in practice, we're probably talking when you save all telemetry at sort of kilohertz speed on a large scale system, we're talking about on the order of a few terabytes per hour, which in this day and age is it's something that can be done. I think relatively easily for a few nights of data. The post-processing computation is of course a different challenge, which is also challenging. And so those are the things that they do give us some headaches, but I'm sort of focusing my talk on future capabilities, so I didn't talk too much about that.
Okay, wonderful. Thanks, Olivier. So I guess for the sake of time, we should move to our next speaker, which is an invited talk. So we will have Marcus Casper from ESO. Marcus, are you around?
Yes,
okay.
I'm here.
So
I hope you can hear me. You should be able to see the screen by now, correct?
Yeah, if you can turn on your camera.
Okay. For that, I need to bring back the Zoom window, which I don't know how to.
On the top, if you just
okay, stop share. Now, okay, now it comes back. Start video. Okay. So now I need to share again.
Yes.
Oh, I'll be done.
Okay, wonderful. So let's go ahead.
Great.
Marcus, so thank you for accepting the invitation. So go ahead.
Yeah, it's a pleasure. So I'm talking today about extreme AO R&D that we are doing a view of the ELT Planetary camera and spectrograph called PCS instrument. And I mean, this is on behalf of a number of people that are actively working on these R&D activities, both inside ESO and also in the community. You can read the names down there. But for the let me just see. Okay, change. For the ones who don't really know ELT, planetary camera, a science case, what we plan to do is we want to characterize nearby Earth-like exoplanets. So it's not really about finding them, it's more about visiting known targets and characterizing them. And what we plan to do is to combine extreme adaptive optics and high resolution spectroscopy or high dispersion spectroscopy. And so the time scale for the ongoing activities is that they are lasting probably until around 2025, when would be the earliest possible start of the PCS instrument project. So we are currently only in the R&D phase, and then the first flight should be roughly some 10 years later or so. So this science I've just been talking about is a noble goal, but you could ask the question whether it's actually also feasible to do that. And to look at that, we have developed a very rough sensitivity model for the instrument. So we assume the XAO and high dispersion spectroscopy combination that gives you a very good contrast, but on the other hand, it also uses a lot of photons, and you spread the light over lots of spectral channels. And so transmission is an issue in the number of photons that you have. So what we are assuming is a 30 hours observation. So we assume an instrument transmission of 10%. We have a spectrograph with a spectral resolution of 100,000, observing the Doppler shifted spectrum of the planet surface between 800 and 900 nanometers. And what we see is that we can observe planets down to about 22 to 27.5 magnitudes in I-band. And these limits really depend on the residual stellar halo noise. So a bright star close to the star, we don't reach, it's more like the 22 magnitude case. When we go on a faint star where the stellar halo noise is pretty low, and we go a bit further away from the target, then we go down to the delta magnitude, to the 27.5 magnitude. So for the planets, we assume occurrence rates that have been derived from Kepler statistics. There are a number of papers for different stellar types and planet types that provides the power laws. We assume a geometric albedo of 0.3, randomly circular orbits, randomly oriented, and we consider only planetary systems where the planets would be dynamically stable. Stellar sample consists of 243 nearby AFGK M stars, and the result of this analysis and of this Monte Carlo analysis suggests that we would be able to observe roughly 100 exoplanets, out of which 10 are in the Earth to super-Earth size regime. You can see the histograms down here. 25 are sub-Neptunes, and lots of them are Jovian planets. And so these numbers look realistic, also because if you look at already known exoplanets in the solar neighborhood, so there are databases that lists all the known planets, and you estimate the contrast and the angular separation of these targets, we already come up with 60 targets that we can observe with PCS. So this looks all good. The concept that this is really a strawman concept designed or prepared to be teared down later in a real instrument study. So this is more or less what the AO system will look like. We have a first stage SCAO system using the ELT M4 running pretty slow. And then after that, we have a high-speed extreme adaptive optics system, and then instruments at the moment, considering 3 types of instruments: low, medium resolution spectrograph, high resolution spectrograph, looking for the oxygen band, and also an imager and polarimeter. And at ESO, the R&D that we are doing is really focusing on these green boxes here on the extreme adaptive optics system. So on the cascade AO and the predictive control in particular, and that's what I will be mostly talking about. Just the list of R&Ds that needed. So this is something that I quickly wrote down, came into my mind. Yeah, for such an instrument, lots of areas of R&D needed. Wavefront sensing, different wavefront sensors. You have low wind effect, you have segment phasing, pedaling, the detector technologies, which type is the best coronagraph for our system, and so on and so on. But again, I mean, we are looking here in this talk only into the XAO control part, and I have also one slide on the deformable mirror developments that we plan to do. So why is the AO still requiring R&D? And the main reason for that is, as I've mentioned, that the main error source or the main noise term is the residual light from the stellar halo. You see here all the AO error budget, that the different terms that drive the stellar halo flux that produces photon noise, and you can see that it's small angular separation, where we are mostly interested in the time delay error, time lag, and the photon noise of the wavefront sensor are the most dominant terms. So these are the ones that we really want to beat down. And because in the photon noise limited case, also the required observing time is proportional to the PSF contrast that we get in these areas. So the goal is really to improve the contrast and the required exposure time by a factor of 3 to 10. And well, if you remember, I considered 30 hours, a factor 10 more or so, then we are in the 100 to hundreds of hours regime, and then it really makes a difference between the feasible and the non-feasible observations. And to illustrate the effect of the time delay error, here's some on-sky images with sphere obtained in a relatively low wind, so slow atmosphere. So you see a nicely symmetric correction halo here by the DM. And if the wind is high, you can see this elongated structure here, this plume of light that adds photons and adds noise. So one thing you can do if you want to beat down the time delay error is, of course, to run the system faster. And this deformable mirror, secondary deformed mirror technologies, that's not always possible. In the ELT case, for example, the M4 can be driven with up to 1 kilohertz, so we cannot go faster with this device. So we need a second fast stage to beat down the temporal error. And the most simple approach is that you just put another adaptive optics system. You see here a second stage with its own wavefront sensor behind the first one, and you let it run faster to beat down the temporal error. And so in a PhD of Nelly Chepawura, we have studied theoretically such a system. So you can see here the rejection error transfer function of several AO systems. So the blue one is the first stage running at 1 kilohertz. The red dotted one is the second stage running at 4 kilohertz. And this green curve here is a combination of the two. So this is what you get out after the cascade AO system. And it's pretty close to a double integrator rejection transfer function running at 4 kilohertz. But there are two notable differences here that I wanted to point out. First of all, you have the noise amplification here of the first stage at relatively high temporal frequencies, which make it hard to correct for the second stage. So this makes basically the error rejection a bit worse in this frequency regime. And you also have the efficient compensation of the low temporal frequencies here. So the speckles at low frequencies are really well corrected. So you expect also an effect on the speckle lifetime. And both effects we can see in numerical simulations. So here's a noise amplification. If you would have the first stage standalone, then an integrator gain of the first stage of 0.2 would be optimum in a high noise case here. But if you have the second stage as well, to get the best overall performance, you have to reduce the gain of the first stage. So you have to put it instead of 0.2 to 0.12 to not amplify noise at high frequencies where the second stage cannot correct for it anymore. So the criterion is really this trail at the output of the system and not at the output of the first stage. On the speckle lifetime, we can also do a statistical analysis of the speckles in the image plane of the two-stage system. You can see that speckles after the first stage have a correlation in time that lasts for a significant amount. Actually, this goes on, and there's still correlation after a few tenths of second delay, while the double integrator behavior of the cascade AO system will really let the speckles decorrelate very quickly. And so this is also a beneficial thing for high contrast imaging. So you don't have to wait very long for the speckle pattern to average out. In terms of contrast, you can see here the effect that you have, the PSF after the first stage, a coronagraphic PSF. So you can still see that there is a significant amount of flux close to the star. Then you can add the second stage. In this case, the first stage is a Scheck-Hartmann. The second stage is a non-modulated pyramid. You see that you are already starting to do quite a bit better in the central part. This is shown here by the yellow curve. And here the main effect is that this is produced by aliasing. So the pyramid wavefront sensor is less affected by aliasing. So you correct some of the aliasing that the first stage still sees, and you produce a contrast gain here. But then a big drop comes in if you run the second stage at 4 kilohertz, and you really improve the contrast almost by a factor of 10 with respect to the first stage correction only. So if you do not want to just run the system faster, you could think about additional alternative ways to control your AO system. And one thing we have been looking into particularly is machine learning, reinforcement learning for adaptive optics. So we have here a machine, a little robot that really looks at the state of the system. The state is composed of mirror signals and wavefront sensor measurements, several steps into the past. And this robot applies an action to the DM based on the state it observes. So the next step, it applies the action. And the robot needs to do good. And how does it know when it does good? You have to define a reward, a criterion that tells the robot, oh, now I have done well, or now I didn't do well. And this reward could be, for example, in our case, we use a very simple reward, is the residual wavefront error as seen by the wavefront sensor. So now let's look a bit more into the detail what the robot is doing. So first, it's building a dynamics model. So a dynamics model means it's a model that predicts the next state, given the current state and the actions it is going to apply. There's a reward, and then you need a planning. You need to find the best action that maximizes reward. And in the first attempt, we have implemented a planning algorithm that basically optimizes the actions in an iterative scheme to maximize the reward. And if you do that, you can see that this machine learning-based reinforcement learning control for AO shows a really great promise. It outperforms the integrator, and it does that because it predicts the wavefront. So this is really confirmed something. We have looked into the time series of signals, and we see that there is a prediction happening. It's almost insensitive to misregistration. So you can see that on this plot here, when you start to shift your wavefront sensor with respect to your DM, because you continuously look at the results of what you are doing and you analyze them in chunks of every 5 or 10 seconds, you actually compensate for these errors automatically. So it's self-calibrating. There's one downside. The inference time of this planning algorithm is relatively long. So because you iteratively try to find the best compensation, and this could turn out to be a problem on the ELT scale. But there's a remedy to that, and you can speed up the model-based reinforcement learning with a technique called policy optimization, and we dub this method now PO for AO, so it's policy optimization for adaptive optics. So the idea is that you replace the planning algorithm by a policy, and this policy is simply, let's say, a step where you take the last state, and it automatically gives you in one step the best action that maximizes the reward. So it is kind of similar to just a reconstruction matrix that you have in an adaptive optics system, where you go from wavefront sensor measurements to mirror commands. But here in this case, you do that by using the dynamic models. You invert it somehow and use neural networks for that. So conceptually similar, but in practice, how you do it, it's a bit different. So what we can reach with this method is inference times of less than a millisecond for either VLT scale systems like Sphere or ELT scale systems. So this method is really fast, and it works either on the VLT or on the ELT. The training times that are needed to really to develop the policy and make the system outperform the integrator controller is less than 10 seconds. So you close the loop without knowing anything about the system, no interaction matrix, no nothing. You wait for 10 seconds while the system plays around, and then it starts to become better than the integrator control. And the method therefore follows on these time scales in environmental changes. The contrast curves that you can see here, the factor 3 to 5 contrast improvement was observed in simulation with a real pyramid wavefront sensor reconstruction and some modal filtering. And down here, when we don't use a real wavefront sensor, when we simply project the phase onto the mirror actuators, a factor of 10 to 20 improvement in contrast, that small angular separations could be achieved. And This is, for comparison, the ideal correction. So that would be simply when you take the measured phase, you project them on the actuators and subtract them directly, instantaneously, without noise. So that is the best, perfect system with a DM, limited by DM influence function strategy. So in the summary, the policy optimization method features a self-calibrating method. It's predictive, it's robust to noise, and it can correct for unexpected errors, potentially. This is, of course, something we have not yet tried. So it looks great, and it's we are very excited about doing further experiments with that. And moving from simulations, we make use of the Magellan MAC-AOX system that is currently in a COVID-related hiatus at the Stewart Observatory, Tucson. So it's bad for MAC-AOX and for science, but it's good for us because we can use the time to do some experiments there remotely. And so Yalo and Sebastian Haffert have implemented this method on the 11x11 woofer. So the turbines in this case is injected by the deformable mirror. The loop is closed. And what you can see here is a coronagraphic PSF with the integrator control and with the PO4AO. And obviously, you see that the stability with the machine learning control is much better than with the integrator control. So the residuals that you see here are limited by NCPA. So this is something, of course, that the wavefront sensor doesn't see. So also the PO4AO doesn't correct for it. And the variance in this case is reduced by a factor of 5 or so, if I see it correctly in this plot. Okay, so we are also now moving to a little bit of something else. We are also planning to do lab experiments at ESO. And for that, we have built a test bench. It's called GHOST. It's GPU-based high-order test bench, adaptive optics test bench. And so this bench features a spatial light modulator from MICADO, which can inject turbulence at 420 Hertz. So we basically, with a high resolution, including aliasing a very high spatial resolution wavefront, we can replay it, and then we use it to drive the AO. And the deformable mirror that we have on the bench is a Boston Micro Machine mirror with DM with 492 actuators. We use a pyramid wavefront sensor, which is not shade redesign. It's at ESO in the lab since more than 10 years because we've used it for another experiment before. The only thing that we have done is we replaced the wavefront sensor camera by a new CMOS type 10 gigabit Ethernet camera. We have a PI modulation mirror here, so that everything is basically set up, and what's missing still is the RTC software. So we are currently in contact with ANU to negotiate a contract for an implementation of the Cosmic RTC platform on our GPU server. And there's also some activities by David Jensen's at ESO, who is starting to try to implement the Durham real-time computer platform called DARC on our computer. So here I have a few movies to show what the bench is actually doing. On the left now I replay some turbulence with the SLM. So you can see here in the image camera how the speckle stands around, as it would be the case on sky when the turbulence would be pre-corrected by a first stage. So here the phase screens come from a simulation. Then here you see the deformable mirror that replays the first 300 carbon F modes. You see here how the speckle pattern with the spatial order of the KL moves outward. So it's a nice illustration of what the correction radius of the DM is. So the higher the order of the mode, the further out is the area in the PSF that is affected. And here you see movies on the pyramid wavefront sensor with modulation and without modulation on the right side. It's also nicely illustrated how the system works, and also it's a visualization of the higher sensitivity that you get when the pyramid is not modulated, because the contrast of the structures here is increased by quite a bit compared to the modulated case. Other R&Ds, so I have just a couple of slides on that. So we also, this is something we have not yet started, but what we would really like to do, if we find the money for it, is that we built a scale 1 prototype for the PCS deformable mirror. So this would be a development with Alpao. You can see here already a phase sheet of the correct size. So these things exist. Alpao has already worked on integrating their control electronics into the mirror housing. So that's a very nice feature, because this deformable mirror with about 20 centimeters diameter. All the electronics could be in the housing, so you only need an optical signal directly connecting to the DM case without having all the high voltage cables and channels going to the DM. So for this mirror, the main challenges are the high actuator count, obviously. So we were looking for something like more than 13,000 actuators on this mirror, and we want to operate them at high speed. So control frequencies of the order of 3 kilohertz, and the response time of the DM should be accordingly high. And we have also, we request sub-nanometric resolution, so better than 0.1 nanometer roughly. And this is needed to control speckles at the level of contrast that we are aiming at, so 10 to minus 6, 10 to minus 7 or so. So the other thing I wanted to mention is that we eventually would also like to test these methods on sky, and there are currently is a consortium that considers upgrading the sphere instrument with a second stage adaptive optics system called Saxo Plus. And the goal in our case for PCS R&D would be to test new control approaches on sky. This Saxo Plus activity as a proposal is not yet approved, but the main features would be that it will use a fast pyramid wavefront sensor in the near infrared, so most likely a CRAD1 camera with a Saphira detector. It would use probably a Boston Micro Machine mirror with 24 by 24, 32 by 32 actuators. And of course, the idea would be, if this works well and we get nice results with this upgrade of sphere, the facility, this capability will be offered to the astronomical community after that. So this is something that's just about to start, and first light at the moment is foreseen for about mid-2025. So this is already bringing me to my last slide. So I have my summary of the main points I want you to take away. So ELT PCS is expected to characterize nearby exoplanets and reflected light down to Earth size in the mid-2030s. We have about 100 potential targets that have already been, or let's say, that we are expecting to be able to observe, and a large chunk of these 100 has already been identified. Maybe there will be more to come. Then the PCS concept generally exploits extreme adaptive optics and high dispersion spectroscopy. And our current AI R&D efforts aim at mostly DM development and the cow and predictive control to reduce the AO halo and the observation times. And what we have identified as a very promising way to control the XAO system is reinforcement learning. The simulations, as I've shown, are under the way. Lab testing has started, and on sky testing is foreseen in the future. And I will stop here. Thank you very much.
All right. Thank you, Marcus, for this wonderful talk. I mean, it's very enlightening of things that are showing up pretty soon, some of them. So we have some questions. One of them is that if the predictive control law is testable on a sphere.
If they? It's okay. I see the question myself. So Jeff Sauvage asked whether the predictive controller testable on sphere. It will be testable only after the Saxo Plus upgrade. The main problem at the moment is that the sphere RTC, I mean, as well know, Sparta is not capable of implementing the machine learning algorithms. So I think these kind of tests will have to wait until we have, let's say, a more novel RTC on the bench, on sphere.
Another similar question related to the predictive part is if you're using model gain optimization.
For the integrator, we are using a global optimization, so we do not use model gain optimization, also not the OMGI, but we are let's say scanning through the gains and use the ones that work best, both on the bench and also on the simulations.
All right. So Jean-Pierre is making another question, which is, can the fast second stage have fewer actuators than the first stage?
Yes, and actually, in the case of Saxo Plus, this is what is foreseen. So the current sphere DM has 40 by 40 actuators, and the second stage that is added to it, as I mentioned, has either 24 or 32 by 32 actuators, most likely. So it will have a lower number of actuators, but run faster. And that is also the case that we have studied in simulations, in the simulations I've shown. In the PCS case, it will most likely be different because M4 has less actuators than the DM that we are considering for PCS. So there it's the other way around.
All right. I do have some questions regarding, you were talking about the reinforcement learning thing, and I don't know if you can have some further comments on it. I mean, do you see, you were mentioning the problems of the inference time, but do you foresee that these will be solvable, I mean, in the near future, 5 years from now?
Yeah, I think what I've shown. So when we started with this planning algorithm, so we have this iterative scheme to try to identify the optimum action. That was not that fast. So there we needed about 100 milliseconds on a relatively low order system for that, but not with, let's say, with cutting edge hardware, but with simply a notebook GPU. But with the policy optimization method, we can, even on a relatively moderate hardware, we can already reconstruct the actions from the state in less than a millisecond, and we can do that for 40 by 40 system and even by 120 for 120 by 120. I mean, it uses convolutional neural networks, and it's as fast as a matrix vector multiply. So this thing is already, let's say, from this point of view, could be brought on Sky now, tomorrow.
All right. Wonderful. So let's thank Marcus again for his wonderful talk, and thanking him again for accepting the invitation. And I would like to stress that you guys can keep asking more questions in the Discord channel we implemented, so that there's plenty of discussions happening right now. So hopefully then Marcus can answer over there, and we can have more relaxed discussions about it. So thank you so much for it. It has been a very nice day of 15 presentations plus our invited talk. So it's been a very dense workshop, but it has been a pleasure to have you all around. We have had an average of 100 participants and people watching our stream. So it's been very good. So we hope to see you tomorrow at 10 a.m. our local time. So please check the schedule for your own time, and see you tomorrow. Thank you so much again. Bye-bye.